In my video on exponential functions, we looked at the relationship between the terms in an exponential function and their effect on the corresponding y values. In addition, we graphed exponential functions from a table of values. However, using a table of values to graph an exponential function can be time-consuming. It is important to know the general nature and shape of an exponential graph. The actual values that may be plotted are relatively few, and an understanding of the general shape of the graph of growth and decay can help fill in the gaps. You may recall that an exponential function is a function with a power in which the variable appears as part of the index or exponent. The exponential functions have the form y equals b to the power of x, or y equals a multiplied by b to the power of x, which can be written y equals a times b to the power of x, where a and b are both greater than 0, and b is not equal to 1. If b is greater than 1, the function is increasing, we have growth. If b is greater than 0, but less than 1, the function is decreasing, and we have decay. I have separate videos on this. In this video, we'll look at the effect of changing b and a on the shape and location of the graph. Let's consider the exponential function y equals 2 to the power of x. In my video on exponential functions, we constructed a table of values and used it to draw the graph of the function. We found that as x increased by 1, y was multiplied by 2. Let's look at what happens when we make x smaller. When x equals negative 10, y equals 2 to the power of negative 10, which is approximately 9.7 times 10 to the power of negative 4, or approximately 0.001, which is a pretty small number. We can slot this value into our table. Now let's look at making x an even smaller value. When x is equal to negative 100, y equals 2 to the power of negative 100, which is approximately 7.9 times 10 to the power of negative 31. We can slot that value into our table. If we graph these values, we observe that as x becomes large and negative, the graph of y equals 2 to the power of x approaches the x-axis from above. However, it never touches the x-axis, since 2 to the power of x becomes very small, but never 0. An asymptote is a line that a curve approaches as it heads towards positive or negative infinity. Let's consider the exponential function y equals 2 to the power of x. As x becomes large and negative, the graph of y equals 2 to the power of x approaches the x-axis from above. However, it never touches the x-axis, since 2 to the power of x becomes very small, but never 0. We say that y equals 2 to the power of x is asymptotic to the x-axis, or y equals 0 is a horizontal asymptote. We also say that as x approaches or tends towards minus infinity, y tends towards 0 from above, and we write it as x with an arrow pointing to the infinity sign, comma, y arrow pointing to 0, with a little plus sign to indicate that it approaches from above. Let's consider the family of curves of the form y equals b to the power of x, where b is greater than 0. First, let's consider y equals 3 to the power of x. The y-intercept is 1, the horizontal asymptote is y equals 0. Second, let's consider y equals 10 to the power of x. The y-intercept is 1, the horizontal asymptote is y equals 0. Now let's consider y equals 0.7 to the power of x. The y-intercept is still 1, the horizontal asymptote is y equals 0. However, this time the graph is decreasing. Finally, let's consider y equals 0.2 to the power of x. The y-intercept is still 1, the horizontal asymptote is still y equals 0, and the graph is decreasing again. The y-intercept is 1 for all of these equations, the horizontal asymptote is y equals 0, and b controls how steeply the graph increases or decreases. If b is greater than 1, the function is increasing. The larger b gets, the steeper the graph. If b is between 0 and 1, the function is decreasing. The closer b gets to 0, the steeper it gets. Another way to look at this is the closer b gets to 1, the flatter the graph gets. Let's consider the family of curves of the form y equals a multiplied by b to the power of x, where a is greater than 0. First, let's consider y equals 3 to the power of 3x again. The y-intercept is 1, the horizontal asymptote is y equals 0. Second, let's consider y equals 2 multiplied by 3 to the power of x. The y-intercept this time is 2, the horizontal asymptote is y equals 0. Finally, let's consider y equals half multiplied by 3 to the power of x. The y-intercept is 1/2. The horizontal asymptote is still y equals 0. The y-intercept for all of these equations is a. The horizontal asymptote is y equals 0. B equals 3 and is the same for all of these equations, therefore they are all the same steepness. For the general exponential function, y equals a times b to the power of x, where a and b are greater than 0 and b is not equal to 1, the y-intercept is a. The horizontal asymptote is y equals 0. B controls how steeply the graph increases or decreases. If b equals greater than 1, the function is increasing. If b is between 0 and 1, the function is decreasing. We can sketch the graph of an exponential function using the y-intercept, the horizontal asymptote, and 2 other points on the curve. Let's try to match some equations with the correct graph. Remember, b controls the steepness. If b is greater than 1, the function is increasing. B is between 0 and 1, the function is decreasing. And a is the y-intercept. For the first equation, y equals 1 to the power of x. 1 to the power of anything is 1. Therefore, this has to be c, which is a straight line. For the second one, y equals 3 to the power of x. 3 is greater than 1, so this function is increasing. A is 1, therefore the y-intercept is 1. This must be b. Now we have y equals 4 times 2 to the power of x. Remember, a is the y-intercept. That is 4 in this equation. There's only one equation where the y-intercept is 4, and therefore it must be e. The next one is y equals 1/2 to the power of x. B is less than 1, so the function is decreasing. There's nothing changing the y-intercept, so it will be 1. This must be d. Finally, we have y equals 5 times 1/2 to the power of x. Again, the function is decreasing. This time a is 5, so the y-intercept is 5. This has to be a. Let's sketch the graph for the exponential function y equals 3 times 2 to the power of x. Remember, we can sketch the graph of an exponential function using the y-intercept, the horizontal asymptote, and 2 other points on the curve. The y-intercept here is 3. The horizontal asymptote is 0. If we find 2 other points, say when x equals -2 and 1, y equals 0.75 and 6 respectively. As x increases by 1, y is multiplied by 2. B is greater than 1, therefore the function is increasing. We can use this information to sketch the graph. First we plot the y-intercept, and we know the horizontal asymptote is y equals 0. And we plot our other 2 points. And now we draw a line through our points, but the line must never cross the horizontal asymptote. And then we sketch the graph. Given an accurate graph of y equals 2 times 1/2 to the power of x, we can estimate the values of y for various values of x. Let's use the graph of y equals 2 times 1/2 to the power of x to estimate the value of when x equals -1/2, y equals 3. When x equals 0, y equals 2. When x equals 1/2, y equals 1.5. In summary, if we can find the y-intercept, horizontal asymptote, and 2 other points in the curve, we can use this to sketch the graph of an exponential function. Thank you.